Okay, we're going to talk about some graphs of functions today. We'll use the vertical line test, which you've already talked about, to see if it is a function. We'll talk about zeros, determine intervals of increasing, decreasing, relative maximum, minimum, and we'll do average rate of change. Also even odd functions. So that's a big section, a lot in it. So first of all, the graph of a function. Let's take a look at this one. Let's talk about the domain here, and we'll find some function values at -1, -2, and then we'll talk about the range. Okay, so the domain. My domain is just my x values. Now, since I have dots here, that's just saying we're not gonna talk about the rest of the function. Now, obviously, usually this looks like part of a sine function or cosine function where, it would keep going. But since I have these dots here, we're just gonna talk about the domain from this point up until this point. Now, the domain here would be from this point -1 to this point 5. We can include -1 because that's a closed circle, but we don't want to include 5 because that's an open circle. So our domain is just my x values here, from here all the way to here. Okay. Range now is my y values, so this range would go from -3 to 3. So I would say -3 to 3, and I can include those points because that's my lowest point, that's my highest point. Okay, the function values f of -1 is 1, and f of -2 is f of 2 is -3. Okay. All right, next, let's talk about zeros of a function. Okay, zeros of a function are where y is 0. All right, so let's do an example. We'll do 3 different examples. Y is 0 is the zeros of a function. So I'm going to look at the first one, a here. The question is, when is this one 0? Well, I know I could graph it. I know it's a parabola that opens up. It's got 2 zeros. I could graph it, I could use the quadratic formula, I could complete the square. I've taught you how to solve these equations, so have your other math teachers, but the quickest and most efficient way to find zeros is to factor if you can. So let's try to factor. This would be 3x, this would be x. Let's try -5 and +2, and that will work. That factors just by guessing and checking we got the first time. So now I'm going to set each of these factors equal to 0. Okay? So you set 3x minus 5 equal to 0, and you add 5 to both sides and divide both sides by 3 to get 5/3. So x equals 5/3 is this 0, as well as x equals -2, because that's when this factor is 0, and 0 times anything is 0. So we just have to look at when the factors are 0. Here's my 2 solutions for the first one. Okay, I won't check this with the calculator, I won't graph this and see if these are actually the zeros, which I know they are because I trust the algebra that we've done. But you're more than welcome to graph it and do second calculate 0 to check these. Let's try this one now. Part B. I want to find out when this function is equal to 0. All right, so what I'm looking at is when is this equal to 0. So you could square both sides, but what you're looking at is when is this equal to 0, because the square root of 0 is 0. Okay, so when is this equal to 0? Well, let's subtract 10. All right, and that gives you x squared equals 10. Square both sides, and you get x equals plus or minus the square root of 10. Okay, so this thing is 0 whenever x is positive square root of 10 and negative square root of 10. Algebraically is the only way to solve this. Because if you try to graph it, I'll graph it for you and show you. Okay, so if you graph this function and take a look at it, you might think that the zeros, it looks like they're at like -3 and 3. And you can even check by doing second calculate value at -3, for example, and see once what that is. But no, at -3 it's 1. So you won't find these zeros in the calculator. You can do second calculate 0, you won't find them. You can look at your table, you won't find them because they're irrational. The calculator can't give you an irrational number with its method, with its approximation, So you're only going to be able to solve this one algebraically. All right. Now let's take a look at the last one. The last one, I want to find out when it's 0, so 0 equals 2t minus 3 over t plus 5. Where it's 0 is where the numerator is 0. Okay, now you can multiply both sides by t plus 5 if you want, but you're going to get 2t minus 3 equals 0. Right, so we're concerned about where the numerator is 0. Now if you add 3 to both sides, divide by 2, you can find the zeros at 3/2 or 1.5. All right, that's the 0. Now if you graph that in the calculator, you'll see that this is a hyperbola. It's got a vertical asymptote at x equals -5, which you would expect because that's where the bottom's undefined. And then it's got a 0 right here at 3/2, 1.5. And you can find that in the calculator as well by doing second calculate 0, right, which we've done. Or you can look at the table. So definitely different ways to get this, but algebraically is going to be our best bet. Okay, let's talk about increasing, decreasing, and constant. A function's increasing whenever its y value, if x gets bigger, the y value also gets bigger. So let's take a look at a couple of examples of this. Here's 3 functions that we've got graphed here. This one's increasing everywhere. Okay, for every x value that gets bigger, y also gets bigger. You know, any points you choose this point, choose a bigger x point like this point, the y value is bigger for each and every point on this. So we would say it's increasing from negative infinity all the way to infinity. Okay, for the first one. Now the second one, increasing, so we'll do decreasing and constant. Okay, so the second one's increasing where negative infinity all the way to -1, including, you can include -1. So, you know, all the way from here, all the way up to here, any of those x values, the function is getting bigger for y. So we would say it's increasing from negative infinity to -1. Okay, it's also increasing from this point all the way up to positive infinity. So I would say from 1 to positive infinity. It's also increasing for any of these x values, the y is getting bigger. It's decreasing from -1 to 1. Okay, and here in the middle, it's decreasing for all of these points. And you can include the endpoints as well, because it is decreasing for -1 and the point that's slightly bigger than -1. Okay, it's never constant. But this last one is increasing from negative infinity all the way up to 0. Okay, you can include 0. And then it's constant from 0 to 2. And then it's decreasing from 2 to positive infinity. So that's what we would say for each of these. Okay, relative maximum or minimum are points that are a minimum for a certain interval. Okay, and the book will say that as well. Maximum, same thing. It's a maximum for a specific interval, but not for the whole function, because there is a point that's higher elsewhere. But it's a relative maximum in comparison to other points around it. So let's take a look at an example. This is a relative maximum here. It looks like at -1. And this is a relative minimum here at 1. Okay? But I also want to find average rates of change. Okay, so this is the function f of x equals x cubed minus 3x. I want to find the average rate of change between 2 points. The average rate of change is just slope. So the average rate of change between -2 and 0 is just the slope between those 2 points. So what we're going to do is take those 2 points. One's -2, and the other is 0, 0, and find the slope. I'm going to take y2 minus y1 over x2 minus x1. Okay, just use these points, 0, 0, and -2, -2. This gives me 2 over 2, which gives me 1. So no matter what point you choose as x1, y1, and you can switch that up. You can switch the 2 points up. Either way, you're going to get a slope of 1 for this line right here. All right, now let's do the average rate of change from 0 to 1. So from 0 to 1, the average rate of change is the slope between those 2 points. So slope is y2 minus y1 over x2 minus x1. This gives you -2. So the slope of this blue line is -2. That's average rate of change. Okay. Instantaneous rate of change is the slope at a tangent point. So the instantaneous rate of change at a certain point is the tangent line, which we would need calculus to do that. We would find the derivative of this function at a certain point to do that, which we're not going to talk about derivatives for now. And instant rate of change, you'll talk about that in calculus. Okay, next let's talk about even and odd functions. Okay, we have some tests, some algebraic tests for even and odd functions that we're going to use. I'm going to put these in the formula sheet. So for an even function, we know f of -x is going to equal f of x. So let's write that here. F of -x is going to equal f of x. Okay. For an odd function, like this one, we know f of -x is going to equal negative f of x. Right? So odd functions are rotationally symmetric about the origin. So you can rotate them 180 degrees and they're going to land back on top of themselves. Okay? Even functions are symmetric about the y-axis. So they're going to be reflectionally symmetric about the y-axis. So any point over here, like this point here, it's also going to be reflected over the y-axis and be on the function on the other side over here. So to do these algebraic tests, the real simple ones are these. So odd, this is an odd test. We run this. What we do is we take this function. This function's, let me use the right notation. This function, let's say, is g of x equals x cubed. This function, let's say, is g of x equals x squared. So what this tells me is that when I stick in negative x into the domain of my function, so that'd be g of negative x, I should get back out negative g of x. Okay, so when I stick negative x in, I should get negative the function. All right, so let's do that. When you stick in negative x, you get negative x cubed. Now negative x cubed stays negative, so I get this. Which if you look at this, this is equal to negative g of x. Right, because g of x is just x cubed, the negative sign's out front now. So what I just showed is that g of negative x equals negative g of x, which is what this says. You know, a function, if you stick in negative x, you're going to get negative the function. I just did that. I put in negative x and I got negative the function. So that would mean this is the work to show me algebraically that it's an odd function. So I would say, therefore, this is an odd function. Okay, these three dots mean therefore. All right, let's try this one then. This one should be even, so I can run the even algebraic test on it. So when I stick in negative x into the function, I should get the function back out. So let's do that. Stick in negative x. Now when you square that, you get x squared, which is the original function. So what I just showed is when you stick in negative x into g, into the function, you get the regular function back. So here, when I stick in negative x, I should get the function back for an even. And sure enough, therefore, this function's even. Okay? This is the work that shows me that this function is even. And it makes sense, you know, when you stick in f of x and f of negative x. So here's the point x, f of x, over here, for example. And this would be the point over here, negative x, f of x. So whether you stick in x or negative x, you're going to get f of x either way. So that's why this algebraic test works. Okay, so part A here, let's try a different one. Let's try to see if this function is odd. All right, it says it is odd because when you stick in negative x, you get negative the function. Let's check that. When I stick in negative x for x into the domain of this, I get negative x cubed minus negative x. Now, if I simplify that, this turns into negative x cubed plus x, which you can see if I factor out a negative 1, this is then x cubed minus x. This is the original function, x cubed minus x. So this turns into negative 1 times g of x. So you can see that I just showed that g of negative x gives me negative g of x. And that's the test right there to see if it's odd. Therefore, this function is odd. And this is the work that shows that it is odd. It just shows that when you stick in negative x, you get negative the function, which is exactly what the test wants us to do. So it is an odd function. Let's try an even one. Okay, so this one should be even. So when I stick in negative x into the domain of the function, I should get the function back out. So let's try it. When I stick in negative x, I get negative x squared plus 1, which if I simplify is x squared plus 1, which is the original function, h of x. So I just showed that this is true. When I stick in negative x into h, I get out the function back, h of x. So therefore, this is even. This is the work that shows that. So if I graph the first one, the odd one, this is what it looks like, x cubed minus x. It is odd. It's you can connect any point x, y to its counterpart, negative x, negative y, and those points will go through the origin. Or you can rotate this function 180 degrees and it'll land back on top of itself. Okay? This function would be even, which means that it's symmetrical about the y-axis. Any point over here would be reflected over the y-axis and land back on top of itself over here. All right, I hope this helps. We'll do some homework problems and record those as well.